Welcome everyone. Good morning or good afternoon or good evening, depends on where you are located. Introducing myself, my name is Islam Mantawi, an assistant professor at Rowan University who will be moderating today's webinar. Today's research seminar is part of the educational and workforce development and the technology transfer activities at IBT ABC-UTC. IBT ABC-UTC is University Transportation Center funded by USDOT to advance the frontiers of bridge engineering, bridge technologies, and accelerated bridge construction. Today's presentation, entitled 3D Printing Using Ultra-High Performance Concrete, will be presented by Dr. Atorod Azizinamini. Dr. Atorod Azizinamini is the director of IBT ABC-UTC and also the director of Infrastructure and Innovation at FIU's Office of Research and Development. Along with Dr. Azizinamini, Ali Javed, a Ph.D. student at FIU, will also be presenting. I would like also to introduce Paul Wiles, who will be moderating the Q&A session. Paul Wiles is the former Georgia State bridge engineer. Welcome, Paul. I also want to introduce Kathy Crowell, who will help organizing today's seminar. Cassie is the co-director of technology transfer at IBT ABC-UTC. I would also like to thank Suri for coordinating the web room. Now, I will turn the presentation to Dr. Atorod Azizinamini and Ali Javed.
All right, thank you. Thank you, Ayam. And thanks for the opportunity to align with one of my PhD graduate students, Ali Javed, to give a presentation. We are very excited about some of the work that we are doing in the 3D printing area. And I have several graduate students that work in this area and hope that we can at least provide you with the overview of and the highlights of some of the activities in this space. So one item that I would like to mention is that the material that you will see that will be presented by myself and Ali Javed also are mainly material that I will be the portion that I will be presenting is also the work of the several other graduate students that work in different bridge engineering projects that we have at IBT, ABC-UTC, and the 3D printing. So I wanted to acknowledge the names of the students, the work of which you're going to see in this presentation, the portions that I will be presenting. And these are Muhammad Fahim Afzal, who is a PhD candidate, Ms. Fatemeh Akbari, again, PhD. All the students that you see here are a PhD candidate. Nirma Kaluk, PhD candidate, but she's already defended her dissertation. Carlos Sosa Carnes, Morgan Dickinson, Sepe Farid Mardani, and Ali Javed, who will be giving part of the presentation today, and Suri Shahabi. So, a couple of things before we move on. First of all, the name 3D printing is an additive manufacturing are synonymous. Sometimes you hear additive construction. So when you hear 3D printing, additive manufacturing, additive construction, these are the same term. And the reason that we are using we are not using a 3D printing in most presentations because it's a copyrighted name, but additive manufacturing, additive construction are a generic name. One thing that we should notice is that the 3D printing, at this in the bridge construction, is still at the very earliest stages. So questions like quality, QA, QC, there are many questions that still needs to be answered through the research projects. So although we have made lots of advances in this area, but yet there needs to be many more research that needs to be done. But some aspect of it actually is ready for field application, as I will introduce. There are several ways of really 3D printing. I have listed here layer by layer. That's the most common one, where you basically deposit layer by layer of a material of your choice during the 3D printer, using a 3D printer that you utilize. There's also extrusion. Extrusion really is like a slip forming, in a way, that you can say that you print a cross section, and you can almost print any kind of cross section that you want. Now, some people, the Shotcrete or pneumatic, also they categorize that on the as a form of a 3D printing. So in a way, you can say these are the three main ones. We have some other projects that we are conducting in the 3D printing, and these are the three main ones that we are addressing them. When you do a 3D printing, you have to have a material. Now, you can print actually a metal, using a metal. You can print using a plastic or other materials. In our case, for bridge application, we are using ultra high performance concrete as a print material. The ultra high performance concrete that we use, now Ali will provide you with more details of it. It does include steel fibers, and it is an open source. When I say open source, it means that the recipe is available for everyone to use. But nevertheless, the UHPC that we are using, it's an open source. The cost is much lower, and it does include 2% of steel fibers, very similar to steel fiber that you use in a regular UHPC for, let's say, closure joints and so on. Now, at FIU, what we are doing, we are looking at our objective is to use the 3D printing as a tool to facilitate construction of the concept that we are developing. Also, it is important to note that some of these concepts that we are going to share with you, it is really also applicable to other structure types too. So it really doesn't have to be just to 3D printing of the bridge elements. You can actually do the same thing for the, let's say, buildings and so on. So it has a universal application. I will give you one examples. I think the examples usually are a good way trying to show a concept, basically. One of these examples is what we call as the UHPC shell. What the concept of the UHPC shell is, that lean itself toward the 3D printing, is basically you are replacing the formwork with the UHPC shell that can be printed. Now, there are many advantages of doing that. In fact, people have done, you see the upper right-hand side, there's a bridge that the cap beam, actually it's a normal strength concrete, cast in place normal strength concrete. It's a formwork that is casted, they bring to the site, they put a steel cage inside, and then they fill it with the regular concrete, and then they connect the elements together. Now, in our case, we are using a UHPC shell, and we are printing them. So the bottom right-hand side, you will see the concept basically is that you print these different elements, you bring it, it can be cast in place, but we are doing a 3D printing. You connect them. We have done lots of work in the connection area. I will show you some of the results. And then you put the steel cage, and then you fill it with the concrete. Now, so the UHPC shell in this concept replaces the so-called temporary woodwork or metal formworks, okay, and facilitates the construction. What's important, the UHPC shell becomes a permanent part of the structure. So you don't remove it, it just becomes, it bonds with the concrete that you put inside that, and becomes as an integral part of part of the finished product. That even that small thickness of the UHPC shell that you're providing, it adds significantly to the strength of the member. As a result, it allows to reduce the member size. And then the cavity within the UHPC shell can be filled with even a lightweight concrete that results into the reducing the dead load. And because nothing really penetrates through the UHPC shell, because it's the rapid chloride permeability number for UHPC is extremely, extremely low, and it can basically, it becomes almost maintenance free. These are some examples. These are some examples that we have printed. Ali is going to provide a little more details with this. This is a beam that was printed using an extrusion process. These are the just schematically showing for a circular column. Ali is going to show you the 3D printing of a hollow column, actually with the steel, longitudinal steel, and the transfer reinforcement inside of that. On the right-hand side, you see a printed section of a formwork for a short span bridge. I will provide a little more information on that. And as I was saying, even the very small amount of the UHPC shell that you're providing, it adds significantly. What you are seeing in this diagram, there's two curves. These are the load deflection of a two beam. The red one is a rectangular beam that is made entirely with a normal strength concrete. The black line is a load deflection curve for a beam that has a UHPC shell and then filled with a regular concrete. Both of them, both beams, have exactly the same dimension, except the black line has a UHPC shell, so certain part of it is made of the UHPC, and it becomes a permanent part of the finished structures. Now, as you can see here, that adds significantly to the strength. See how much strength you gain from using that, basically replacing a formwork with a UHPC shell that becomes a permanent part of the structures. So at this point, I'm going to turn it to Ali Javed, who is going to be giving his portion of the presentation. And then I will come back later to show you some additional 3D printed concept that has done with other students.
Thank you, Dr. Azizinamini. So, good afternoon, everyone. My name is Ali Javed, and I'm a PhD candidate at FIU, working under the supervision of Dr. Azizinamini. So, I will be discussing two projects on which I have worked. One is Robotics and Automation in Accelerated Bridge Construction projects and Robotics Bridge Construction Experimental Phase. So, as Dr. Azizinamini mentioned that we are using ultra high performance concrete for the 3D printing applications. Ultra high performance concrete has superior properties. According to Federal Highway Administration, it has a very high compressive strength as compared to other cementitious materials, usually more than 18 KSI. It has a very good tensile strength, which range usually between 0.9 to 1.5 KSI. It also provides very good modulus of elasticity, which range between 6 to 9 KSI. And again, the ultra high performance concrete has very low chloride penetration, and it has a very high resistance against freeze and thaw. And on top of that, it's a flowable material, self-compacting material. So for the 3D printing applications, as ultra high performance concrete is a very flowable material, so it becomes very difficult to perform 3D printing with the conventional ultra high performance concrete. So what we did here, we basically modified the mix design and reduced the flowability of the mix. And on top of that, we introduced heat curing at an optimum temperature. So the benefit of heat curing, it basically reduces the open time of the UHPC, which gives an optimal window to work with the 3D printing of the material. And on top of that, it also increased the buildability of the printing material, which allows to print taller and wider sections of the material. Now, for the development of the material, we actually did a lot of mixes, tested a lot of mixes, and some of them are shown here from mix 1 to mix 8 on the basis of the workability of the material and the flowability of the material. So these are the composition shown here for these mixes. And for all of these mixes, mostly the binder to aggregate to binder ratio was kept as 1, and the 2% volume of steel fibers were used for all of these mixes. So the mix which is shown, which were shown in the last slide, the flowability values for these mixes range between 5.5 inches to 10 inches. Now here, two main properties were observed. One is the flowability, and then the workability of the material in terms of 3D printing application. An important criteria for the ultra high performance concrete is the material mechanical properties. So the compressive strength of all these mixes was evaluated by performing 28 days test on the cylinders. And it can be seen that the mix 7 yielded a maximum compressive strength of 21.18 KSI. It yielded a high compressive strength, but the flowability was 9 inches, which was not suitable for the 3D printing application. So mix 6, which showed a good combination of both high compressive strength, more than 18 KSI, and also a low flowability, approximately 7.5 inches. So we used mix 6 for the 3D printing application. So when we heat the material, it becomes very important to optimize the heating time of the material. So to optimize the heating time, a simple setup was prepared by using strip heater that's shown here, and a material was heated at different temperature to select the heating time for this material on the basis of the shape stability and shape retention. And it is shown that, like, if we heat the material up to 100 Fahrenheit, the open time is quite high, which is approximately 45 minutes. And as we increase the temperature, the open time reduces. Like for 250 Fahrenheit, it can go up to 5 minutes only. And when we heat the material, obviously it affects the properties of the UHPC. So it was the compressive strength was performed on cubical specimens to see the difference in the compressive strength of heated ultra high performance concrete. Two different curing conditions, ambient and wet curing condition, were introduced for these specimens, which were heated from 100 Fahrenheit up to 225 Fahrenheit. And it can be seen in the wet curing conditions, the reduction in the strength of ultra high performance concrete is very less. And for specimen which were heated at 125 Fahrenheit, the compressive strength can be achieved more than 16 KSI. So after selecting the mix which yielded a good compressive strength, low flowability value, and the effect of open time was studied. So for a fresh UHPC, the flowability is 8.1 inches as shown in this table. And as we observe the time at 10 minutes time interval, the flowability of the mix, it reduces, and up to 1 hour, the flowability reduced from 8.1 inches to 6.1 inches. So basically, this effect of open time on this mix gives a very good window to work with the 3D printing. Now, as Dr. Azizinamini mentioned that we are doing different 3D printing applications at FIU. So different kind of mixes were used for these applications. Like, sorry, for conventional construction, the mix which was used, it had a flowability of 9.8 inches. In the middle, this is the mix composition of the mix which was used for the extrusion applications and for the layer by layer application. Both of these mixes do not have any viscosity modifying agents, but the mix which is being used for the Shotcrete applications, viscosity modifying agent was also introduced in it, and this is the mix composition of the mix for Shotcrete. So moving towards the 3D printing of first beam shell elements. So we developed a 3D printer which can do 3D printing of beam shells. And in the beginning, a beam shell was used with a height of 12 inches, width of 13 inches. The wall thickness was kept as 1.5 inches, and each section of the printer was 6 inches, which was printed in one segment, and it was heated up to 125 Fahrenheit temperature. To move the printer, the heating time was given as 25 minutes. So it took total 8 hours of printing time to 3D print an 8 feet long beam specimen, which is shown here. So this is the final specimen, which was 3D printed by using section printer developed at FIU. Now, to see the behavior of this printed specimen, a similar cast in place specimen was also constructed, which is shown at the bottom here. So both of these specimens were, the reinforcement cage was placed inside them and filled with normal concrete. And a third specimen with same dimensions and same reinforcement ratio with regular concrete was also prepared and tested for 3-point loading in the lab. This is the loading setup. As you can see here, the beam is placed, and the hydraulic ramps were used to apply the load on top of the beam, and the beam had a simply support with an effective span length of 7.5 feet. These are the tested specimens. All three concrete beam is shown on the top, and you can see that there are quite distributed cracks in the concrete beam specimen, and at the middle the cast in place specimen is shown, and it has one large crack in the middle on the UHPC shell, and at the bottom the 3D printed UHPC shell beam is shown. And again, if you can see, the behavior of both cast in place specimen and 3D printed specimen is quite similar in terms of cracks. They both had one large crack in the middle. So this is basically the tension surface of all three tested specimen. Again, for the concrete specimen, we can see a lot of distributed cracks and the failure pattern on top. And in the middle, this is the cast in place specimen. Again, it had one large crack in the middle, and this is the relative slippage between the concrete and the outside shell, which can be observed because there was no mechanical connectors in this specimen. And at the bottom, we can see the 3D specimen. Similar behavior was shown in the 3D printed specimen. Same kind of relative slippage was observed for 3D printed specimen, and the failure pattern was also same as cast in place specimen. So if we see the difference in the load deflection curves for all three specimens, we can see that for the cast in place specimen and 3D printed specimen, they both exhibited a high load carrying capacity as compared to concrete specimen. Both of these specimens exhibited approximately 20% more strength and approximately 40% more ductility. Now, this beam, 3D printed beam specimen did not have any reinforcement inside the UHPC shell. So after this, what we developed a 3D printer for hollow column, which can have longitudinal reinforcement and transverse reinforcement. So this is the animation of the conceptual design of the printer, in which the printer is basically the nozzle head assembly is fixed at the top, as you can see on this right, for the injection of the material, and the build plate on which reinforcement was placed is moving from top to downward. So as the printer moves downwards, it prints a section. So this is the time-lapse video of 3D printed hollow column, which was printed at FIU. And you can see that the nozzle is fixed on top. The material was actually injected inside this nozzle and the printer was moved downward. So with this printer, we printed a 14-inch by 14-inch section of hollow column with 2-inch wall thickness of the shell. Each section was 5-inch height and it was heated at a temperature of 125 Fahrenheit. And 25 minutes of heating time was given to each section before moving to print the next section. And with this particular printer, we could actually print a hollow column up to 72 inches. And it's not only for this particular rectangle square nozzle. Actually, the nozzle head can be replaced with any other shape, rectangular hollow column or circular hollow column, and those can be printed by using the same concept. So far, by using this particular printer, we printed a 66-inch tall hollow column, and it took 6 hours and 15 minutes of printing time for this printer. This is the final 3D printed hollow column specimen, and as you can see inside the printer, and when we remove it from the printer, this is the cross section of the column, which shows the inner core, and these are the longitudinal reinforcement and square spirals which are coming out of the shell, which were introduced inside the printing process. So again, to study to see the behavior of this hollow column against cyclic loading test, a similar cast-in-place specimen was constructed by using the same reinforcement ratio, and both of them are placed side by side to we can see the cross section of both of these columns. So these are the final specimen for the cyclic loading testing, and the both hollow column were fabricated. The footing was constructed by using a pocket connection with the UHPC, and the cabins were installed on top to apply the axial and cyclic loading. So this figure shows the testing setup for this 3D printed hollow UHPC column, and the axial load was applied by using the hydraulic jacks on top, and the lateral load was applied by using a servo actuator, 150 kip servo actuator on the side. The results of this experimental test will be published soon. The next part will be presented by Dr. Azizinamini.
All right, thank you, Ali. So, as you see, one item that I should add that, like Ali said, that he did quite a bit of a study in the heating the concrete, and the reason for that was to establish, trying to see what is the maximum heat that we can apply to the through the printer, actually, to the printed section without adversely affecting the mechanical properties, short term and long term. And so that was a reason for to do it those ways. So what I would like to do is just briefly to show you some of the work that other graduate students that are working in the space of the 3D printing, that is in progress. Some of these concepts again are ready for really the field application. One of them is by one of my PhD students, Mohammad Fahim Afzal, who hopefully is going to graduate in spring of 2024. And what he's doing is really printing the formwork for short span bridge. Now these formwork can probably go to up to, we are thinking about the 40 to 50 feet. Right now we have some design for 40 feet, 50 feet. What you see on the upper right hand corner, that's a printed section. This is one section. You put them adjacent, side by side, basically. The printer that Fahim is using is on the lower right hand side. You see where my mouse is. Basically, this is a printer head that moves from one end to another, and the end product is what you see over here. This is This is one of the printed sections. Again, you print several of them and you put them side by side. So this one is a 12 feet long deck. It's 3 feet wide. The heating time was 25 minutes, and total printing time was fairly long. Now, I must say again, the 3D printing of these kind of stuff are at the very earliest stages. We are right now trying to develop the automated way of trying to feeding the material to the printer head. That's an ongoing project. So hopefully within a year or two, the amount of the time is going to be reduced significantly. The other thing that you have to keep in mind is that with the 3D printing, you can print these things basically 24 hours a day if you want to. The printers don't ask for it overtime. So here's the sequence. So you print these sections, and then you put them side by side. Actually, you have an exterior and interior section. I'm only showing the two interior sections. So what Fahim is doing, basically printing these sections, and in fact, he's going to build a one short span bridge and then test it. So you put it here, and then the next stage is that once you have it, then you put the steel cage basically in there, the steel cage, and then you fill it with the concrete. So he has come up with a way of trying to basically how to connect these things without really adding any mechanical actions or anything like that. So you put the steel cage in the formworks, and then the next thing is that you fill it with basically a concrete, and that's the completed. So for short span bridge, it's just a formwork that is printed using a UHPC shell. It does have some steel reinforcement, so you can pick it up, transport it, and so on. Another graduate students that we have is that graduate Nerma Kulak was working on this was actually using printing a block that has an various application, probably I would say MSC walls, maybe even, or to build the habitable structures on the moon. So she was working also on a project that was with the NASA, trying to build the habitable structures on the moon, but using some of the technologies that we have on Earth, basically. This is a printer head, basically, that the printer head that Nerma had. So there's a cavity here. That's where you deposit basically the UHPC, and then it's within a gantry, and that printer head can move. It can have 6 degrees of freedom, so you can really print any shape that you want. But she was interested to print the block that you see down here, and all these edges that you see is to have these blocks basically like a puzzle pieces to come together. These are block. One of the application that Nerma had was to basically to build the blocks to facilitate construction of structures on the moon. And the idea was that because it takes a little bit of time, but you can print continuously these blocks and then put it aside, and then with the robots you can pick them up and then basically place them on the on where you want, and then complete your structures. Another students that I have, PhD student Morgan Dickinson, is working on a Shotcrete. Again, Shotcrete, some people puts it as a form of a 3D printing. What I would like to say is that really there is a automation, and a 3D printing is a subset of the automations. So the Shotcrete could be categorized as automating really the construction process. He's also using a UHPC, but he had to modify the UHPC in order to be able to Shotcrete. The material that Morgan is using for Shotcrete does have a fiber. So it's exactly the same open source UHPC that Ali showed this ingredient. but with some modification, because in the shotcrete you have to be concerned about the elastic rebound and not to lose so much material. So here is some photo. Morgan has done lots of experiment. He's looking at after he has a shotcrete, he's looking at the bond between the shotcreted UHPC and the substrate. He's looking at the fire resistance of the material. He's looking at the tensile, basically he's doing taking some cores and doing some direct tension tests, trying to see the bond between the shotcrete and the regular concrete. The surface condition, what kind of surface condition you have to have, what kind of exposed aggregate you need to have. So all that is part of the study that Morgan is doing. This is just a very short video. I hope that it kind of shows you what's going on. Actually, the student that you see is Fahim. So this is a shotcreting. This is actually one of the early shotcrete experiment that we did. Now Morgan has really advanced this thing to the point that it goes much smoother. Here the hose is being held by hand, but Morgan has developed something that basically automatically holds basically the hose and then moves it left and right. Another student that I have actually worked on the retrofitting the timber piles using a UHPC. This retrofitting really, what Carlos is doing is looking at using a timber as just a formwork. So the finished retrofitted timber column, you do not rely on any strength to be added from the timber, because you can have lots of cavity, you can have lots of void in there, lots of damages that there's no way to estimate what the contribution of the timber pile could be. So that he doesn't rely on the capacity that is provided by timber piles, but it's just that UHPC that is wrapped around this. Now, the wrapping of that, again, that's an extrusion process that we are looking at right now. So using an automated process is trying to wrap basically the timber piles using a UHPC. I have 3 other students that are working on the space of trying to retrofit existing concrete columns using a UHPC. This is some examples of it that you see. Again, the idea is that you have a normal strength concrete, you add some reinforcement, you add transfers, basically a reinforcement, and then you wrap it basically with UHPC. This is an ongoing project. We are hoping to publish some of these results, hopefully within the next few months. And then also working on the automating the process. Again, that's going to be like a slip forming. The slip forming really is extrusion or the slip forming that you have. And this is I just also wanted to show the printers that we have. Everything we build our own printers. There is nothing that we purchase it. We don't buy a printer. We fabricate, manufacture our own printer. The nozzles are customized for a specific application. The nozzles have heat elements, and then it has a mechanism to make sure that the UHPC that is deposited is not sticking to basically the nozzle. Okay, and then so path forward really, if I want to summarize it, the market is going to take care of itself. It is not that whether we like the 3D printing or we do not like the 3D printing. The 3D printing is going to come. It has found its way to many different industries. The construction industries has been a little bit slow to pick it up. But again, because of the economy, because of the labor shortage, that we are experiencing in the construction industry, I think the 3D printing is going to be the next frontier, and it's coming. It's used for with different materials. Nowadays, we can use the 3D printing with the metal. It has tremendous amount of the potential to significantly reduce the construction time and even produce a very high quality finished product. It's at the earliest stages, but the advances in the 3D printing is really moving forward at the exponential manner. The other thing that I think that we are keeping in mind is that when one looks at the 3D printing, you should not be looking at the 3D printing by simply replacing the human with the robots. The printers can print any complex shape. Some complex shapes could be a more optimized form of a construction that cannot be done by the human, but it can be done very easily with the robots. So the 3D printing really allows us to optimize the shape, print any shape that you want, and those final shapes may not be very easy for human to do. So that's why we are saying that we should not be really looking at the 3D printing as simply replacing the human with the machine. We should be looking at it as an opportunity to come up with a better and optimized shapes that are better suited for the robots and the machine to do it. And finally, this is our final slides. Most of the technology that you saw done here are already, for example, 3D printing of the hollow columns or the formworks for the different application is ready. Some industries have expressed interest to work with us, but we are looking for partners to implement these. The US DOT is very interested in the implementations of these technologies. So if you see any idea, any technology that you would like to be partner with us to take it to the market, please just send me an email. It's very easy to find me. My email is aazizina@fiu.edu. So with that, really, that's our last slide, and we will be happy, myself and Ali, to answer any questions that you might have.
Okay, thank you, Dr. Azizinamini and Ali Javed for the nice presentation. And now I'm going to hand the mic to Paul Lyles to moderate the Q&A session.
Thank you, I.M. And we do have a few questions that came in ahead of time, and we have a few that have come in during the presentation. And I'm going to go ahead and get into those questions now. The first questions we have here came in beforehand, and this is about the process. And the first one I have is, do you have issues with bonding between printed layers since they cure at different times? And is any surface preparation required between layers?
Let me take a shot at that. The columns that you are seeing, okay, these are like an extrusion process. We have not used a layer by layer. Most of ours is a kind of like an extrusion process, and in the extrusion process, you have less problem with that. Now, right now, we are in the process of trying to develop a continuous feeding of the material to the printer head through the nozzle. Once that is done, really it will be the nozzle will be moving at a continuous speed, so you won't have any problem with that. But at the present time, if you print a, let's say, 6-inch section and then stop to mix the concrete and then proceed, then you will have some issues. Layer by layer does have issues with the bond between the layers. That's why we are not really using a layer by layer printing method. We are using more of an extrusion section. But in the layer by layer method, the question of the bond between the layers is not really resolved yet with respect to short-term or long-term mechanical properties and so on.
The next question we have is, how is the quality assurance performed or specified for 3D printed UHPC or maybe other printed concrete elements?
Yeah, so as Dr. Azizinamini mentioned in the presentation that 3D printing in the bridge construction is still at its early stage. So currently there are no quality assurance measures, but I mean at FIU also Dr. Azizinamini is working on a project. So hopefully in future we will have some quality assurance measures as well.
Okay. The next one was, have these structures been tested to see if the pores result in a structurally homogeneous section as they appear to be poured in layers?
I think the question that they're asking is that if a 3D printed structural element behaves the same as, let's say, cast in place version of it. Ali has done the comparison like he was showing. Do you want to show these? Maybe you want to elaborate on these?
So as I showed this load deflection curve, so basically if we see at the strength point of view, there is no difference between cast in place and 3D printed section, both strength and ductility point of view. But yes, there is a little bit of difference in the stiffness of the member, as a cast in place member shows higher stiffness as compared to 3D printed section.
Let me add to what Ali is saying. There is I think the questions that mainly they're asking is that, okay, if I have for example, here you have a cast in place, and this is a printed section. What is the difference if I test these two columns like this under the axial load and the lateral load? Am I going to see a difference? In the case of the hollow column, actually, we haven't published the results yet because we are still reducing. We actually saw in the case of the hollow column, actually having a layer by layer, I mean, having a printed, it may have some advantages. We will elaborate. But really, we have not seen that much difference between the two columns that were tested. So they both are pretty much the same. In fact, the printed one, for the reason that we need to explain in the journal paper that will be published, was advantageous in this particular case.
Okay. The next question we have is, please comment on the development of the 3D printers and their potential future commercial availability.
Let me take a stab on that one. As I mentioned, we are constructing our own 3D printer, and we would welcome. In fact, that's one of the areas that we would like to partner. We can develop printer actually for almost printing anything. And when I say anything, it's not exaggerated. We have a system of what kind of the concept of the nozzle that we are using is universal for our application. How the nozzle should move, we have again the universal concept that it can be customized for different applications. Like for example, the ones that Ali was showing, we have printers for the formwork for short span, printer for the blocks, printer for the hollow columns. So we can develop we can fabricate and construct and design printer, 3D printer for any applications. There is no limitation with respect to that, really, the full scale. So, and it is, in fact, I think it has lots of room in the market.
Okay. I have a couple questions about the beams here, and these came in during your presentation. The first one was, what is the thickness of the UHPC shell?
Yeah, so the thickness of UHPC shell is 1.5 inches, and the total width of the specimen is 12 inches.
Okay. And the second part of that question was, were there any shear tests done on the sample beams?
No, there was no. I think what they are saying is that the shear test on the beam, no, it was just a 3-point loading that was done. Okay, I may add one thing to this item, and I think this is something that we have started. There is when you cast a normal strength concrete, okay, inside the UHPC, bonding of a normal strength concrete to UHPC is a different issue than bonding a UHPC to normal strength concrete. So we do have a solution for that, but it was not presented here. You do need either certain type of deformations or mechanical devices that bonds the hardened UHPC to normal strength concrete. So that issue you need to understand. But as far as the behavior of the beam goes, structural behavior up to the failure point, really there is not that much difference between the two. But at the failure, close to failure, you will see some differences. But those differences can be diminished if you make sure that there's a good composite action between what's inside the shell and the UHPC. Again, we have not really shown. We didn't show lots of results over here, but the complete answer to that question really demands sharing some additional research results that we have.
Okay. Another question on the beam was the person said they weren't sure exactly what they understood on it, but it says you print the beam shell, the external faces of the beam, then you fill that volume by pouring the concrete in it. If that's the case, what is the real benefit of the 3D printing as opposed to maybe just a traditional way of making a beam?
Well, I mean, sometimes it's very, if you have, first of all, there's many advantages. Let me go back to here. I think, I mean, first of all, you don't have to form it up. It takes a time to form up, to remove the form. So using a UHPC shell, it's a form of an accelerated construction. And the second thing is that UHPC shell becomes a permanent part of the structures. Even that the small amount allows you to significantly to reduce the member sizes. What's inside of the UHPC shell is protected for life because nothing penetrates through it. The cavity could be filled with the lightweight concrete. The member size gets smaller, the total dead weight gets smaller, the foundation size gets smaller, and it has economy. And it becomes almost maintenance free. And then, as over here you see, how much strength do you get basically by using that shell? So it has a tremendous amount of benefit. And more than anything else, I think, is the fact that it's a form of an accelerated bridge construction, really, because we haven't shown that here, but we have developed the connections on how to connect these different units together.
Okay.
So yep.
We'll look some now about the UHPC mix. The first question I have here, this came in beforehand, was did you use a proprietary or non-proprietary UHPC mix in your 3D printing? And you've gone to this slide. Go ahead.
So as Dr. Azizinamini mentioned that we have used open source UHPC, so it is called as non-proprietary UHPC. So the recipe of the mix is available to be used by anyone. Yeah, so these are the different composition of different UHPC mixes which we have chosen.
Okay, and all right, that's fine. Then let's look at another one here, and it says, how do you manage the steel fiber component of the UHPC mix? And is there any potential for the nozzle to jam with the steel fibers?
So that's basically one of the main advantage of using extrusion process or section printing, that it incorporates the steel fibers inside. And obviously we had many challenges in the beginning, in the development stage of the printers, because these steel fibers or the UHPC, it usually makes a very good bonding with the nozzle itself. So we come up with solutions, and in the end we develop these printers in which we are not facing these issues anymore.
And then also, if I may add, if I go to this slide, this is what you see over here is a shotcrete using a UHPC with the steel fibers. So that what you saw over here basically is being Morgan is shotcreting the student actually in the picture is Fahim, not Morgan. But the hose that you see down here really it delivers the UHPC that has steel fibers using open source UHPC. So yes, the question was, it took us really at least about 6 months to solve that problem, so that we don't have basically we don't have the steel fiber to bunch and then jam together. So there's a few things that you have to do certainly, but it's very much doable. So it took us some time to resolve that issue, but it has been resolved.
Okay, we have a question here about is this technology adaptable for heavily reinforced sections? You've got it shown with some rebar in the sections, but if you had a lot of rebar, are the fibers still going to be able to get in there and everything?
Yes, I think it depends on, of course, the application, what you want to do, but I think the nozzle can be adapted to have the member to have any kind of thickness, any amount of reinforcement. The one that Ali was doing was it had a longitudinal, as you can see here. You can explain, Ali, what you had.
Yes, so basically in these hollow columns, we had both longitudinal and transverse reinforcement, and the cover was only 1/2 inches on both sides, and we did not have any issue with the printing process. So yes, it can be, I mean, as Dr. Azizinamini said, it depends on the application, but the reinforcement can be incorporated in the printing process.
We had a cost question that came in beforehand about what is the cost estimate per cubic yard of concrete, 3D concrete?
Okay, let me answer it that way. The open source, I can tell you the cost of the open source. I don't want to comment on the proprietary version, but other than just saying it's very expensive. The open source, the cost of the material, including the steel fibers, can run up to about anywhere between $500 to $800 per cubic yard. So this is just the cost of the material, anywhere between, let's say, $500 to $800 per cubic yard. Of course, there are commercial versions that numbers, some people have given some very high numbers, but you got to remember those high numbers are, in some cases, you have to use certain equipment, technicians, times, and everything else. But I can only comment on the open source because we have the numbers on that, anywhere between $500 to $800 per cubic yard, and it can probably go down even more than a little less than that. And this is using a 2% steel fibers in there that is used in general UHPC.
Okay, we've got some questions that came in during the question and answers, and I'm going to turn it over to IM, and he can pick up there, I think. IM?
Thanks, Paul. The first question is, can the entire element, beam or column, be 3D printed with just one material, either concrete or UHPC? And what is the advantage of the composite member? I think Dr. Azizi elaborated on the second part already. So the first part is, can the entire beam be printed with just one material?
Yes, it can. You can do anything you want, really. I mean, the beauty of the 3D printing is that it is so flexible. You can do anything that you wish in any shape. Doesn't have, the column doesn't have to be just straight. It can take on any shape because let me just give you one example. For example, the ones that this printer that you see down here. This printer, I mean, I can have any kind of a nozzle, and I can have a 6 degrees of freedom, and I can move in any directions, and I can print any shape, and solid or hollow or whatever.
Thank you. The second question is, should there be a need for repair such printed material? Are the repair method different from the cast concrete?
Yeah, we have not really done any work in that area, so I cannot. The repairing a UHPC element really is beyond just a 3D printing. That question is, in my opinion, at least, I don't believe it's been really researched yet.
Then the following question is, how heat curing has been applied and how this can be done in the field?
I will let to Ali later to say a few words. First of all, this 3D printing right now it's at the it's in the closed environment. Number one, and it is done through the basically the printers that we have. It incorporates basically the heating. So it's not the heating is not done by, let's say, an external surface or anything like that. So, but the heating is done within the printer itself. And then the effect of the heating, let me tell Ali to elaborate on that.
Yeah, so basically we used different types of heaters and finalized like strip heaters for the heating of these elements. And the effect of heating I already explained in the presentation. So if like as Dr. Azizinamini also mentioned, if we heat the material up to 150 Fahrenheit, it doesn't really affect the compressive strength of the material.
Okay, the next question, Ali, if you can go to the slide that you showed the load deflection curves for the beam, slide 15 and 29. The question is, slide 29 seems to show difference at the end result in terms of which beam is stronger. Can you comment?
So I guess they're talking about this. So basically, if we see the green curve is for the concrete beam, and then we are basically trying to say here that there is no difference in the casting place UHPC shell beam and 3D printed. So blue and red curve, they're both showing that same behavior. So that's the result of the 3D printed specimen and casting place specimen. And that is one major conclusion, that there is no difference in the strength and ductility of both beams. So the 3D printing method which we have developed here, it's not affecting the strength and ductility of both specimens.
Okay, thank you. The next question is, Washington DOT does not allow Shotcrete to be used as a structural element due to the lack of verification of adequate bonding to the reinforcement. Will be there any research that will evaluate the bonding of the UHPC to the rebars?
The Shotcrete that we have done so far, it's been just to exposed surface of a normal strength concrete, and that is to increase the capacity. We have not done any shotcreting on the rebars, that is basically placing a rebar and then shotcreting. I don't really see any problem with that, but we have not done any work with the having a reinforcement and then shotcrete over that. It's been mainly for the regular concrete with the exposed aggregate, welded surface, and then having about ½ or so shotcreted UHPC.
Okay, last question is actually related to the next IBT ABC-UTC conference. Because can you elaborate when going to be held?
Yeah, our next conference is going to be in the December of the 2024, and that's going to be held actually in Miami, Florida. And the exact date that I can give you is December 11, 12, and 13 of 2024. It's going to be in actually the Hilton Hotel in Miami. We just signed the contract. There is going to be opportunity to exhibit. This conference is going to be, it's going to include every aspect of the bridge engineering. It is not going to be just the ABC, because our new University Transportation Center is dedicated to any technology that helps any type of construction, whether conventional or the accelerated bridge construction. There will be call for abstract that is going to be, please be on the look. There's going to be advertisement in magazine like ASCE, Civil Engineering Magazine, in the Aspire, in the infrastructure, road and bridges. So it's going to be advertised. Hopefully it will show up in January issue of the magazines, call for abstract. And but the main thing is that in this conference we are going to be basically covering every aspect. The name of the conference is 2024 World Bridge Engineering Conference. So it's not, the name is changed to match the mission and objectives of our new University Transportation Center. So it's a December 11, 12, 13, 2024, Miami, Florida, at the Hilton Hotel. And the name of the conference is 2024 World Bridge Engineering Conference. So hopefully, I gave all the information we have right now. Look for call for abstract in January 2024.
Okay, this actually concludes today's seminar. Thank you, Dr. Azizinamini, and thanks, Ali, for the nice presentation. And I would like to thank everyone. I would like to thank the presenters, Dr. Azizinamini and Ali Javed. I would like to thank Paul Lyles for moderating the Q&A session, Kathy Crowell for organizing this webinar, and everyone behind the scene to make this happen. Thank you very much. Looking forward to meeting you in January.